Shall we start?
Hello everyone. It's an honor to invite Haotian Liu for this week's annual ideal seminar. Haotian Liu is a final year PhD student at University of Wisconsin-Madison, advised by Professor Yongjie Li. His research primarily focuses on computer vision and visual language multimodal learning, and his recent work has centered on building customizable and steerable large models that follow human intent, including instruction following multimodal models, controllable image generation, and customizable foundation models. Yeah, and he recently has a series of very popular work on LLaVA model. And yeah, thank you for.
Thank you. Yeah, thank you. Maybe I will just sit and speak. Yeah, thank you for the invite. And it's great to talk about my work during the PhD, Steerable Visual Intelligence. It will look like a job talk, but it's not a job talk, apparently. Okay, yeah. So in the past years, computer vision has advanced very rapidly. In like 2009, when the ImageNet was introduced, it was regarded as one of the hardest data sets ever created for computer vision tasks, and is considered as far-fetching to be solved. And since 2012, when the deep learning really took off, there has been great developments and advancements in the image classification task or computer vision, where back in 2020 or 2021, the top one accuracy of ImageNet validation dataset is already above 90%, which is almost considered as solved. And our deep learning researchers have not only trained those deep models to do image classification, they also learn to detect objects in the image, object detection, and even segment out each pixels that correspond to each objects in the image. All of those models work very well, but they generally fall into a single paradigm, specialist model, where you have a single model and you define your single task, you train on a single data set, and you achieve a single model. It will work very well on the data set or the scenario that you define, but it may not necessarily work very well for other tasks, or it may not necessarily work on a different task. So the question is, like, if we really want to build a real-world application using those specialist models, what are the challenges we may face? And let's consider the simple task where you have a hotel and this is a business center, and like suppose you're a guest and you're visiting this hotel and you want to print a doc. And the question is, can I print my documents here? And let's try to solve this task by using a series of specialist models. So first, we may just think like, can we use an object detector? And before the OpenSet era, like object detectors are usually trained on the COCO dataset, and those are the base models. So to do this proper detection in the indoor setting, we first need to fine-tune and expand the vocabulary into the indoor settings, so that we need to add the sofa, the chairs, the laptops, the computers, the printers. And after we do the vocabulary expansion, the second step is like, we'll ask it to detect the printer. And unfortunately, there's no printer in the image. And if we are fortunate enough to have OCR engine, like it will tell you like what are the texts. OCR basically tell you what are the texts and where they are in the image. And they will tell you like it's a business center and there is a sign here like around some coordinates. And the question is, does it indicate that there's a printer? Well, the answer will be probably, because sometimes or usually there's a printer in the business center. But anyway, like because we're working on the task, we want to build an application for the user, we have to give a final output. And we have a decision model to take in all the responses of those expert or specialist models, object detector, OCR engine, and more. And you will need to give a decision, but it will be hard. It's because there's no agreement between those specialist models. So like maybe it will say yes, but it's not able to give a quite certain answer or give a proper explanation. So we can see that with those specialist models, although they work really well on those each specific domains, but it may be hard or challenging to make them steerable to adapt our tasks that we want to put into our real applications. So my research goal is to build a generalist model that can be easily steered for our need with minimal effort. And this generally contains two parts. One is so that we can customize those models to different domains with minimal human supervision. And we want a model that can easily we want the model to be easily steered by the natural language, which can be super flexible. So the first part, let's try to see how we can make the vision models customizable. And the previous paradigm is to collect those data and train our model on a specific data sets if we want to train a classifier. For example, let's say we want to train a 10-week classifier on these 10 classes. What we will do is to first we define those 10 classes, and then we collect the images for each of the classes, and then we train a classifier on those images and labels, and then we got a 10-week classifier. And if we want to train a classifier on the different data sets, we'll need to do this data collection and labeling and training on the different data sets again. So the question is like, this is not good. And CLIP, it marks the first paradigm shift from this paradigm so that it can build zero-shot classifier just from label text so that you do not need to train. What they do is that you do large-scale contrastive pre-training on image-text pairs, where you have an image encoder to encode the image features, text encoder to encode the text features. And by contrastive pre-training, you will minimize the distance between the image features and the text features that are semantically similar and make those dissimilar ones apart. And after training, and let's say we now want to build a classifier on the 10 classes, what you will do instead of you to train and fine-tune those models on the downstream tasks, what you can do is that you just feed those texts into the text encoder and you will obtain the text features. For any test image, you can also feed them into the image encoder, get the image feature. And basically you will compare the similarity between the image feature and all the text labels, the features of the text labels, and the ones that are most semantically similar will be the classification result. So it makes a lot of sense and it works quite well. And you are able to create lots of different classifiers from the label text as easily as just like by prompting the model to do so. And researchers also find that in order to improve the CLIP's adaptation, you can use either linear probing, full model fine-tuning, or other fine-tuning techniques to adapt the model to on different downstreams to make them work much better. And this, however, somehow goes back to our previous paradigm, because to fine-tune the model, you will usually need a label data set. And so that for different downstreams, you're now requiring them to like fine-tune the model, collect the data, label them, and this somehow goes back to our previous paradigm. So my question is how to adapt those models to downstream tasks without necessarily manually annotating the downstream images. And suppose that we have a pre-trained CLIP model and we want to make it work really well on the car classification task. For example, we want to classify, we wanted it to be able to distinguish between BMW and Audi really, really well. What are the ways that we can improve its performance on this task? But we do not necessarily require the model or requiring the human labeler to annotate the data of this specific domain. And we present React to deal with this, and it's presented as CVPR 2023 as highlight. So let's quickly review like how CLIP classifier is done and what are the information about the downstream are used. One thing is that we use the text labels from our downstream datasets to get our text features, and those text labels actually define what our downstream task is. And the question is, what can we further leverage those text labels to provide more guidance to our models to let the model perform better on the downstream? And one idea is like, just like how we as like graduate student or undergrad student to improve our performance on the exam that's going to take place next day. What we will do is to gather the textbooks that we have already reviewed. We have got all the like exercises we have done. We will review them over and over again before the night of the exam, and we may be able to perform much better on the test. Similarly, we can do the same thing for the CLIP. Let's say we have the CLIP model and we have some way to figure out the relevant samples about the test it's gonna take, like the classification between those cars. What are the ways that we can figure out those relevant materials? And the idea is to use retrieval, where because we have the text labels, we can use text-to-image retrieval, text-to-text retrieval to get those samples that are relevant to the downstream tasks that we have learned, we are going to perform on. So we have the text features, and we can use the text-to-text retrieval to retrieve the images that has the captions that are super relevant to our task. We can also use text-to-image retrieval to retrieve the images are relevant to our tasks. It's okay that our retrieved samples are not correct or are not perfectly aligned. It's acceptable, but because it's associated with the ground truth images and text pairs, so like if we trust the quality quality of the our training data set is higher than our classification model, then it will potentially allow us to improve our performance. So what we will do is to fine-tune our CLIP model on those retrieve the relevant samples and fine-tune it so that it performs much better on this task. And we
I have a
also
question
like
on the previous slide. Hello?
I thought it's Siri.
Oh, no,
Okay.
it's me. Sorry. I have a question on the previous slide. Sorry, I didn't.
Okay. Okay.
Can you go back to the previous slide?
Yeah,
Yes.
sure.
Sorry. So you are going to give some relevant text and you're going to generate the image, or you're going to retrieve the image?
We're going to retrieve the image. So basically, the Leon dataset is the dataset that contains around like 400 million or 2 billion images and text pairs. And those are the datasets that the CLIP models or open source open CLIP models are trained on. And they're image text pairs dataset, and we can use those text labels to retrieve the images or texts.
Yeah, sorry. And what if the retrieved image is wrong?
Yeah.
There's some mismatch in
Yeah,
your
exactly.
text to image alignment. What happens then?
Yeah, so like it is super likely that the retrieved samples are sometimes it can be wrong, and it's okay because we are not saying that the retrieved samples, for example, if we retrieve using BMW, and if let's say we retrieve an image that is actually an Audi, it's okay because we're not saying that the retrieved image is BMW. We will actually use its original caption as the annotation to train our CLIP model. So even if we retrieve Audi when we are acquiring with BMW, we are still using its ground truth texts that are like originally annotated from the the web or human. Yeah.
Yeah, but it seems to be highly relevant to the task, because if like my task is to discriminate between BMW and Audi and I generate like confusing image, or not generate, sorry, retrieve like wrong pairs of images, my fine-tuned model then may be wrong, isn't it? Like seems to be like very relevant to the task.
Yeah, so basically like what we find is that first is that we a large amount of the data are correct. So basically they are about our domain, and there may be a small proportion of the data that are not from this domain, but we can treat them as a small noise, and we believe that the relevance of those cars, BMW, those data are much more than the original like Leon data set. So it at least it will not harm, and it certainly will improve in terms of the car classification for our fine-tuned model. And then it's for whether the retrieved sample have the correct correspondence to our BMW. And as I said, like those data set are actually a subset of the data set that we use to train the CLIP model. So like we're just retrieving the relevant part of it so that we make sure that our model performs really well on this relevant subdomain. And we are not changing the quality of the data set. We are not changing the correctness of the data set, so that the gain will be coming from that the model is more and more familiar with the specific domain, instead of like making the data like higher quality or lower quality in terms of the the correctness.
Okay, thanks.
Yeah.
I have another question about this. So
sure.
when you train this model, a CLIP model, you already use Lion or a data set like Lion, or you're directly using Lion. So are you suggesting that CLIP itself is not well trained or well fit onto the Lion data set because potentially the model size is too small? Or why would this actually help improve CLIP's performance if it actually learns everything about Lion?
Yeah, so that's a good point. So basically, like you can imagine that if a model that models, if you have a model of capacity that's say like 400, for like 1 billion parameters, like if you are using like 1% of the the parameter to memorize about the cars, 1% of the parameter to memorize about those basic feature extraction, and the 98% of the parameter to memorize about all the other semantics that are not relevant to the cars. Basically, what we are suggesting is that if, let's say, you are able to replace those 98% of the parameters to memorize much better on the cars, it can make the model much better. And we have also like some experiments proving that instead of like introducing any new data samples, so that it's not, we are fitting the model better on the Leon data set, It's that we're just let a model that's pre-trained on the layout data set and review part of the data samples in the layout data set. It also improves the model's capability or performance on the specific domain.
I see.
Yeah. Yeah, so actually like this, I hope like this coming slides also partly helps it to better illustrate where like, let's say like what the embedding space may look like after the clip pre-training. Like, let's say we have an image feature and we have 4 text features of BMW, Audi, plane, and cat. After the clip pre-training, it may look like something like this, where BMW and Audi are closer to this image because they are all cars. Planes are slightly away, and the car and the cats because it may be the most different from the cars, so it will be the furthest away. So you may be able to classify the cars, planes, cats pretty well, but you may not be able to classify BMW and Audi super well, and because like they're not super apart, so that the similarity between these images and text may be similar. And what we want to happen is that after the React customization, because in our training data, the planes and cats are much fewer, and the model are now required to distinguish between the BMW and Audi when it's during its contrastive pre-training. And we hopefully we can achieve something like this, where the BMW are still quite close to the image feature, while the Audi label is further moved apart, so that it can perform the classification much better because it learns a better decision boundary on this domain. Yeah, and we also study different training strategies for the customization, where we first find that if we fine-tune the text encoder in the model, usually will deteriorate, the performance will usually deteriorate because we find that the retrieved samples, especially for the text, they're in a much confined space compared to the original like layout text space. So when you're fine-tuning the text encoder on this specific subset, like the text feature it learns will actually become much worse, and the text encoder is very prone to overfitting. So after we freeze the text encoder and we perform log text tuning, where we only fine-tune the image encoder, it actually performs much better. And we find that it generally improves over the model's performance. And based on the same intuition, we believe that it is also possible that our image encoder can be having some like overfitting issue to our downstream, and sometimes the original knowledge may still be useful. So we propose this log text and gated image tuning, where we draw our motivation from Flamingo, where they have gated self-attention layers, so that we, for each of the original self-attention and feed-forward network, we will keep the original weights and also keep them frozen. And we insert additional gated self-attention and gated feed-forward network layers so to adapt to the new domain, so that those new domains are responsible for the adaptation, and the original weights are responsible for maintaining original like feature extraction and memorization capabilities. We conduct our experiments with 10 million retrieved samples of the Leon 400 million datasets, where we first study different pre-training datasets and pre-training model scale from VIT base 3216 and VIT large 14. We also vary between different pre-trained methods, like the OpenAI clip, which is trained on web image text 400 million, OpenClip trained on Leon 400 million, or OpenClip trained on Leon 2 billion images. And we find that React consistently improves over the clip performance. And notably, like for the layout 400 million, like there's no new samples introduced. Just by revisiting some of the samples during the training, the performance can also increase.
Yeah. In my opinion, I think after you retrieval to get this data set,
yeah,
actually, do you think it's feasible if we train a model from scratch from randomly induced like weights? Because in my opinion, those data already contain all the relative knowledge, and if your specific target is only this, for example, image classification, we train from scratch.
I think that's a good question, and I think one thing to consider is like whether those data sets contain all the information you need. Because of the first is that like when we fine-tune the text encoder, it actually becomes worse because it does not necessarily understand like other distributions better. So like at least from the text part, it may have some potential issues, and I believe similar issues may also present in the image encoder as well. similarly, like I guess this is also related to how our like gated self-attention work, where like you freeze the original weights and add additional weights can potentially allow you to work better. So I guess, yeah, maybe it will still work, but maybe it is not unclear whether it can actually outperform.
Yeah, I think at least clip looks like this will give you a robust
Yeah.
starting point.
Yeah.
So
yeah.
I have another question on this. So when you measured your performance on ImageNet, have you compared it with if you fine-tune clip model on the ImageNet dataset?
Yeah, we also like so if we like do fine-tune the image on the ImageNet, is the performance so we have we can compare this in different settings. So first, like for clip, like we are like training the image the clip model on the image text pairs dataset, and then we're customize it on a subset of that. And during this process, we're not requiring any human labelers to label our dataset. So in this process, we can still claim that our model is doing something like zero-shot adaptation, because we're not, except for defining the task by providing what classes that we want the model to classify. We're not providing any like labeling effort. We're not specifically asking human to collect the data or filter the data. So that part is still comparable, and what our numbers are shown is presented here. And if we further fine-tune the clip model to on the ImageNet and annotations, it will outperform the zero-shot React. But in our paper, we also show that if we further fine-tune our React customized the clip, then we fine-tune it on ImageNet, it actually outperforms the clip fine-tuned on ImageNet that's without the customization process. And similarly, on the elevator, we also show that it's true, where elevator is a benchmark of 20 datasets that we collected for the in the wild settings. They also have the training set, and we find that after the React customization, it not only helps with the zero-shot settings, but also for the few shot and full shot settings with both and full fine-tuning. And I hope this answers your question.
Yeah, so basically, I guess the message is not that you don't actually need a human label data set to do it. I think the message is actually this can do something on top of having human label data, or in any other case when there's no human label data. But I don't see why, I don't see it as a replacement for human generated labels or any data set like that, because there's also things like data distribution shift and also data coverage issues that, this retrieval, basically you're biasing it towards the lion data set, which may not be the distribution you care about at test time. So yeah, I because you started
I think
saying
I think this is a good point.
So that was my confusion.
Yeah, I think this is a good point. But as long as you are bringing additional like labeling efforts, or you are considering like the domain shift, I guess like we're not. This is the framework of the React is actually general. Like you are not requiring the model to have to like retrieve from the layout data set. You're not requiring the model to having to do the like retrieval. Like you can. The key is to use our like framework to like get relevant samples, and it can be gathered by retrieving from layout. It can be gathered by retrieving from search engines. It can be retrieved from some databases. It can also be generated from some diffusion models. Like any way that you believe can get a data that's like good for like for your target distribution. Like you can still use the React customization pipeline. And the retrieving from layout is just an instantiation, and we want to use this example to show that it is like first is that it is possible to do so that we show that it is, and it also like echoes with those recent findings that use diffusion models to improve the classification models. So yeah, I think that's probably a fair judgment.
Yeah.
Yeah, and also like we show that it's able to React also helps with dense prediction tasks like object detection and segmentation. So in conclusion, React creates customized vision models with minimal human supervision. And although now we're able
I have
to
a question.
like customize. Okay.
Yeah, so again in this setting, like how do you ensure that the retrieved data is diverse enough, like without any supervision?
Yeah, so like basically we're making sure that the retrieved data are semantically so first like we're making sure that our retrieved data is semantically relevant to our like downstream data sets. And because we are retrieving like around 1% of them, and like theoretically they're like we are already like getting all the subsets of the relevant semantically relevant samples from our training data set. So it cannot be like less diverse than the original like Leon training data set with that of those relevant samples. So I guess like the key is that we are getting the most relevant part of the task that we care about, and we are maintaining the original distribution of the part that we care about, but we do not we also remove those noise that may not help with our model training. And I guess this is the point that we want to make.
Like you remove the noise, like for example, if you say like retrieve car images and it
Yep.
picks out all BMW cars.
Yeah.
So
So
how do you guard against that? Like,
okay, I see the point. So basically like what as we said, like when we are creating our clip classifier, like we're not just saying like we want to create a car classifier. We're defining the clip zero-shot classifier by providing all the label text, meaning that we're saying that we want to create a car classifier that can work on the following 80 classes: BMW, Audi, Benz,
yes.
etc.
And you ensure that it like
Yeah.
spreads uniformly across
Yeah,
all this.
exactly. Yeah, exactly.
But that is where a supervision is required, what I'm trying to say.
It is a supervision that's not required because we are not utilizing any additional information that a zero-shot clip classifier are using. Like the input to the zero-shot clip classifier is like the label text, because without those label text, you're unable to generate those text features. So you're unable to create the classifier. And if you do not believe the clip is zero-shot, then I think this is out of the discussion topic today.
Okay.
But if you believe that clip is zero-shot, then we're not using any additional like
Okay.
then clip. Yeah.
Okay, thanks.
Yeah. Yeah, so okay, so like we now try to fine tune and expand the vocabulary to indoor settings, and this whole system is still not very streamlined. So the question is, how can we further make it more streamlined, and preferably using natural language? And as we are humans, we can see and reason about the visual world and express and interact with natural language. Like the doctors read the CT scans and explain their findings to the patients with natural language. Teachers teach students with conversations with natural language, and we can share our life and findings on the social media and interact with others with natural language. So it would be great if we can have a visual intelligent assistant that can interact, can understand the visual world and reflect with natural language. And we present our first work, visual instruction tuning on Europe's 2023 as our presentation. So the closely related work along this direction are pre-trained image to text generative models, where the model will take in the image as the input and output the text reflecting its understanding. The models generally can perform basic visual reasoning by understanding what's happening in image, what's the image about, while it generally lacks the capability to follow complex instructions or engage in very long conversations. And it's now, time flies. It's back in March last year, OpenAI demonstrated GPT-4 Vision, which has strong visual reasoning capability, where given such an image, GPT-4 Vision is not only able to like identify what's happening in image, locating the objects. When the user gives an instruction like what's unusual about this image, it's able to say that the unusualness is actually the man ironing clothes on the back of a taxi. So it's great that it can perform such complex reasoning while there's no it's not accessible until like several months ago, and there's no disclosure on how it works. So the question is, how can we create multimodal models that can actually follow humans' intent? In NLP, researchers find that instruction tuning in language models allows those large-scale pre-trained language models to adapt to the downstream or like learn to follow the human intent by fine-tuning the model on a small set of instruction and answer pairs like behavior explanation or movie recommendation. And to collect those data, unlike like humans to write those instructions, you can let the models like ChatGPT to generate those instructions at an affordable cost by expanding a small set of seed instruction output pairs, usually a few hundred, to million scale using in-context learning. And this has been used to create powerful open source instruction following language models like Alpaca. And regarding visual instruction tuning, how do we build instruction following large multimodal models? And let's start with this basic architecture. We have an image, we have a visual encoder that can encode it into the visual features, a cross-modal connector that bridge the connection between the visual features and the language decoder so that it can understand what's happening in the image. And the language decoder will also take in the instruction from the user and try to reason about the image and predict what's happening in the image. And what we need is actually like, how are we going to train the model for following multimodal instructions and how to gather those data. And if we take a look at those instruction tuning teachers, those are mostly text only, and there were no powerful multimodal teachers. And even today, like GPT-4V can make silly mistakes that seems to be like silly mistakes that are like human find it to be silly, but super hard for the models. So we try to see what are ways that we can make our annotations like accurate and also like helpful for those multimodal models. And we propose to leverage the text-only GPT to try to create visual instruction following data. And the key is like, how do we let text-only GPT understand what's happening in the image? And we find that in COCO datasets, we actually have those ground truth annotations from the human, where you have the captions, which are image level context, describing generally what's happening in image so that the model can have a sense of what's happening, the context of the image. And you can also have more fine-grained context, which are layout, basically the bounding boxes and object categories, describing like, showing like how the objects are scattered in the scene so that it can provide further details on what the scene maybe look like. And those information can all be provided to the text-only GPT in the textual format so that they can understand, and they provide necessary information for like what the image is about. So we
sorry, in
sure.
your sorry again,
No
this
problem.
is in context learning, but
Yeah.
you are giving the indices or like the coordinates of the bounding boxes in your
Exactly.
prompt. Is that what it?
Yeah, exactly.
Okay.
Basically, we're providing the model exactly the same thing that we're showing here, like person, the coordinates, the other person, some coordinates. Yeah. And
sorry, but what is the task? Like, how does it understand that? Like, what is the latent task that it is you're trying to perform here? Like, does it understand it is like object detection as the task?
Yeah, we'll explain like in the following. Yeah.
Okay.
Yeah. So basically, we're trying to build a text-only data engine, and we are using the image context in the textual format to tell the text-only GPT on what's happening in image. So basically, we will first provide some in-context examples where the image, we're going to convert them into the image context in the text format to basically it will say like, the image is like this with some captions. And also we are going to provide you some bounding boxes about each location of each object. And then this is the image context. And we are going to write some instruction and answers, which should be the output of the GPT model, where the instructions are the question about the image, like what's in the image, what's happening in the image, like what's the image about, and also can you tell me something is in or it's not in the image. And the answer are the derivable answers about the question about this image. Those are the in-context examples. And then we're going to perform the actual inference where for any of the image in the COCO training data set, we're going to convert into the image context in the text format as well, so that now the model can know like what's happening in this new image. And now the task is to generate the visual instructions for this new image. And the model will generate the instructions and answers about this new image, although it's only seen like the image context in the textual format. Basically, those contexts allow it to understand what's happening in the image. And the task is to generate the instruction and answers. And now we can gather the instruction and the answer as well as the original image to create our visual instruction following data, which is a triplet of the image, instruction, and answer. And I'm not sure if it's clear to help understand what we're doing with our text-only data engine. Okay, sure.
So your instructions specifically encodes that object detection, do object detection. Is that like that?
Oh no. So we will show some examples very soon. So basically like the instructions will like this, like what type of vehicle is featured in the image, and the answer will be the image features a black sport utility. Okay, black SUV. And where the vehicle is parked, is parked in some underground parking area. We can also have another response type, detailed caption, like the question is, what's in the image? Describe the image in detail, and the answer will be something like the image is underground parking with SUV, blah, blah, blah. And also like complex reasoning questions where we want the model to be able to reason beyond the visual facts. For example, what challenges do these people face? The model not only needs to understand like there are SUVs, there are bags, there are people. You also need to figure out that because there are so many luggages, they may be having trouble fitting all of them into the back of the SUV. So these are the instruction and answers we want the model to generate.
Yeah, I'm wondering, so you have two sources of useful information. One is caption,
Yeah.
another bound box. So for caption, it's definitely helpful.
Yeah.
I wondered, have you ever conducted any rigorous simulation study to see whether the bounding box help your model generate?
Yeah. So basically, what we are the way we are using those bounding boxes are that in our instructions, we're asking the model to try to generate the questions that about the relevant location of the objects, and also include a question like counting if there are multiple of them. So like those the caption may just say like there are human and luggages in the image, but the bounding box may tell them like how many luggages, like 4 or 5. Yeah.
I think the question is truly do text-only GPT understand the coordinates epsilon y1?
Oh yeah. This we have some like not so rigorous ablation. Like we have another model, Glidgen, where it can convert those it can generate images based on the object locations or like layouts, and we can show that we ask the GPT to generate the object coordinates and layouts of the given some caption, and we can use Glidgen to visualize the generated layouts, and we can find that first is physically makes sense, so that the human is not floating above the desks, these kind of things. And also we can see that if the caption is something like human is on the left of the table or right of the table, the generated coordinates are actually correct. But it's not that rigorous because like we do not do any like quantitative evaluation. But I think there's another paper called Layout GPT or something in Europe did something like this as well. So
I think it's somehow related to SVG.
Yeah.
Any reason you went ahead with bounding boxes and not like segment anywhere, that kind of thing, like segmentation maps? So is it like how you feed in the coordinates instead of something?
Yeah. Because we find that this is the most straightforward way for the model to understand, because like to understand the like left or right of those bounding boxes, basically it's more, you can imagine it as a like mathematical like subtraction to understand, like if it's negative, it's on the left, it's positive, it's on the right, these kind of things. So it may be easier for the model to understand. And there are also follow-up works that further improve this by making instead of just using object categories like luggage or bag, it will also make the like region caption much denser, like a bag with a white bag with some stripes, these kind of things, so that it can allow the generated instructions to be more like visually grounded. And yeah. So like regarding the model, it's more like we choose a very simple architecture where we have a language model, and we have a vision encoder, and we have a projection layer. Where the vision encoder we use clip because we find it to have a very nice semantic space. Language decoder as instruction following model like Vicuna, and the projection layer is just a single linear layer because we can imagine the clip semantics are like a visual foreign language and organized in a different way as a traditional language. and a single linear layer is sufficient to project into a space that the language model can understand. And regarding the training, we have the two-stage training pipeline, where the first stage training, we train the projector only for the on the image text pairs data set, so that the images are projecting to a proper space that the language model can understand. And for stage 2, we fine-tune the language model and the projection layer so that the model is fine-tuned for instruction following capability for understanding the multimodal tasks. And after we train LLaVA, we find several interesting emerging properties. Before that, we first quickly review some of the properties of our training data, where we have mostly common concepts because of the COCO and 63 million. We have visual instructions in English only. There's no human name annotation, and there are no explicit OCR data. And LLaVA is able to perform strong, have the strong visual reasoning capability to understand the unusualness as the man's ironing clothes on the back of a taxi, and it's more visually grounded and detailed than the open source baselines like Blip2 and Open Flamingo. And it's able to understand this humorously parodied Mona Lisa. It's actually a dog in the same pose as Mona Lisa, which where this image is definitely out of the COCO distribution. And it can recognize the NeurIPS 2023 from this image. And also when we ask who will be interested in this, it can correlate NeurIPS with its pre-trained language knowledge that is related to artificial intelligence and machine learning. And also when we ask the question in Chinese, it can properly give a response about the French Quarter and also a brief description. And to evaluate those large multimodal models, because they now give longer responses, we cannot simply just evaluate it with the editing distance, Raj score, these kind of metrics. And we draw our motivation from an NLP, and we find that our data creation pipeline can be slightly modified for the GPT-assisted visual chat evaluation, where you can provide the image context in the text format to tell it what's happening in the image. We have the user instruction and some model outputs, and we will ask the GPT to give the feedback on our model responses, and also give a feedback on explanation on why it gives a score like this. And this can help us better understand our model's behavior. We also design LLaVA bench in the wild, which is challenging, and we provide very detailed annotations about what's happening in the image, some beyond the questions itself, so that we can not only evaluate the correctness of our response, but also evaluate for the hallucination. So in conclusion, LLaVA is an intelligent visual language model that can reason about the visual world and reflect with natural language. And its design is simple and general, that we show that it's possible to adapt language models to multimodal effectively and efficiently. And it can train within one day on a single node, and it's compatible with almost all the optimizations for large language models in terms of both training and deployment. And there are crazy community efforts on large multimodals since the introduction of LLaVA and Mini GPT-4. And in terms of both modality, downstream, different tasks, and also benchmarks to help us better understand the capability of multimodal models. And we also made our own effort, LLaVA 1.5, to further improve the LLaVA's capability. And we find that LLaVA actually excels at participating in visual conversations, that in those benchmarks that require the model to give natural answers, performing visual chats, LLaVA actually outperforms base models outperforms many models that actually are released after LLaVA. However, it still have much rooms for improvements like yes, no, short answer, OCR, all kinds of capabilities. And common explanations on the inferior performance in VQA are that are mentioned in those papers are, one of them is LLaVA does not use resamplers like Q-formers, which can compress the image into a few latent tokens and can potentially better model the visual properties, while LLaVA only use a single linear layer. Well, we believe that because those Q-formers still use the cross-attention mechanism, and because LLaVA optimizes the full language model, so our model has much larger capacity and should have the capability to model the similar geometry relationships using our language model. And so maybe not. And second is about large-scale pre-training, where Q and Blip2 use hundreds of millions of images or billion-scale images, while we only use 600K. So like maybe it's because we do not have large scale pre-training, but actually our language model are pre-trained on 2 trillion of tokens. Our clear vision encoder are pre-trained on 400 million tokens. So 400 million image text pairs. So basically all of them have seen a large amount of the data and they should have sufficient world knowledge. So maybe that's not the problem either. And actually one like key reason that's rarely mentioned is about the academic task-oriented data, which are those VQA datasets that can bring additional visual specific knowledge to large multimodal models. And also like because they're short answer, they are actually easier or cheaper to obtain for the industry players. For example, we can obtain like 400K annotations in VQA V2 datasets in like maybe 4 or 5 years ago already. And we performed scaling study on LLaVA using 3 datasets, one for short answer, one for format instructions, and one for open-ended QA. And we find that just by adding VQA that's already allow the model to perform very well on MME and MMVAT dataset, like almost is almost on par with InstructAblip 14B model. And this is very promising, but we find that there can be some weird and silly mistakes like this. So for example, like given such an image, and if the question is, can you tell me what I can cook with these? Before like adding those VQA V2 datasets, the model will say like, okay, what are in the fridge and what are kind of the recipes that we can you can do with that. And after training with VQA V2, where there are lots of like short answer data, yes, no data, it will answer yes. So I can tell you I have the capability, but I won't tell you. This is something will happen. And this is quite awkward because this is not what we want, because that's not our intent. And we want a model that can follow humans' intent to provide the natural answers when we ask something like this. So the reason of the overfitting to VQA datasets is also quite simple. Like because there are some ambiguous prompts like Q, question, A, answer, in the VQA datasets, and although originally model will output something like the man is wearing a yellow shirt, and maybe a human will also answer something like that. But we're in VQA datasets, we're training it to output something like yellow only. And when we're training it to do so, meanwhile, similar questions can occur in our like natural QA datasets, like what's the color of the shirt, and when we're training that, we are actually asking the model to say that the man's wearing a yellow shirt, a longer sentence. And such disparity can make the model confused, and sometimes for natural questions, it can also give some very short answers. And the solution is also super simple, like just give response format prompts that clearly indicates what your intent is. Basically say like answer the question using a single word or phrase instead of just using Q&A where you do not know whether what's going to do. And we also find that these response formatting prompts have some very desirable properties that are useful for our model. And
I have a question here. Like, are you like saying that more informative prompts are useful for fine tuning?
Exactly, because this can allow the model to know like what format it should output. Its output should be look.
Yeah, and sorry, related question, like, but you manually create these more informative prompts.
Exactly. Based on the on our understanding of the data set distribution.
Okay, thanks.
Yeah, and adding the format prompt allows the model to outperform the InstructAblip on MME and MMVAT 14B already. And we also add additional datasets that are used in InstructAblip. And by just using a subset of its training dataset, less than 1% of its pre-training dataset, and half of its parameters, our LLaVA 7B already outperforms InstructAblip's 14B on all the benchmarks. And we also perform additional scaling to increase its visual knowledge, image resolution, language model, reasoning capability, as well as other datasets. And we denote our final model to be LLaVA 1.5. And its performance, it outperforms InstructAblip Q1 on diverse range of 12 benchmarks. And also, in the meantime, it only uses less than 1% of the training data. So it's super sample efficient. And it also it can be the format prompts can be used to deal with those tricky questions, like given an image of Hawaii, if the question is what's happening in the desert. Sometimes the original lava will say that there's a city skyline in the desert, but if you add it to if ask it to point out the factual errors if they exist, if not just answer the question, the lava 1.5 can I say that there's no deserts in the image. It's actually a beach something, and it can also output the answer in the JSON format. It can also be used to create prompts for stable diffusion of a desirable format just by prompting. And we also find some interesting capability called combinatorial task generalization, where like you can generalize, you can have generalized the capability of some multiple independent training data without necessarily training them together. So for example, if you have VQA data plus some like visual conversations, you will see improved visual groundedness or OCR in the visual conversations. If you have multilingual text-only conversation plus some English-only visual conversation, you can perform multilingual visual conversations. Similarly, longer writing, text-only conversations plus some shorter, more casual visual conversations allow you to see improved writing in visual conversations. And this is super useful in designing our next generation data mixture, that you may not need to create all combinations of the data in your training, and you can let large multimodal models generalize. So the conclusion is LaVA 1.5 is performant and sample efficient. It has been used for control study of data model for large multimodal models, and it can generalize to combinatorial tasks. And we've been working to improve LaVA's visual capabilities in the past, and including like tool use, RHF, visual prompting from Mu, and like all kinds of scalings. And there has been some excuses of being worse than GPT for vision, where like we are not trained on large scale of data, so that and also our image resolution is small, so that it cannot recognize some of the details. It may not be trained on large scale instruction following data set as GPT for vision does, because our domain is mostly COCO, so that it may not be able to understand some of the tasks. And also our language model may not be powerful enough to solve all the tasks. And to deal with those excuses, we did out of curiosity, we tried to increase the image resolution, make the instructions much more diverse by leveraging our user instructions, and also use GPT for vision to give the pseudo label. And also we scale up our language models to 34 billion. And this allows us to build LaVA 1.6 with 34 billion parameters, and it outperforms LaVA 1.5 significantly. And it also matches Gemini Pro on selected benchmarks. And it is the first work that comes from academia that outperforms or matches Gemini Pro on some benchmarks. There are a few like future directions I'm interested in exploring. I'll quickly go over them. Short term is to further improve LaVA's visualization capability, and also to build unified model for generation and understanding, and longer term to build super intelligent models. And for unified generation of image, text, videos, like people have known that those multimodal models are useful for building better image generation models. And also like for, we believe that this is just a very first step by just like giving better captions. And because our multimodal model have a much better understanding on the object relationships, like compositional, like relationships, these kind of things, it can be used as a fine-grained reward model for our diffusion or image generation models, so that it can have a better alignment between the images and the captions. And also it allows for better instruction following for generation and both editing. And ultimately we'll bring all the knowledge we've learned in the image generation to video understanding, and also for long video generation. And ultimately a unified model for understanding and generation. And also OpenAI has some like analogy to be a super intelligent model, where like usually we are building like traditional machine learning models where we human to build some models that are weaker than human. And the super intelligent models, how can a human build a super intelligent model that are stronger than human? And what are the techniques needed to build those models? And the analogy from OpenAI is that can we use a weaker model to supervise a larger model? Like, can we use a GPT 3.5 to supervise the GPT-4 model? And what are the techniques we can learn from there? So basically, we want to see what are the techniques that can be leveraged to build weak to strong supervision or generalization model. And like we believe that in multimodal, there are some interesting analogies. First, how can a language model supervise a multimodal model, where allow you to build a multimodal model without a multimodal teacher for data scarce modalities. And more importantly, it may allow you to build a better model than human. The reason is that we human are expert on videos, on images, on sound, on text, because those are modalities we perceive daily. And what about the modalities that we are not perceiving daily, like the universe or the microscopic cells? And if we imagine those are the out of distribution modalities of human, if we are able to use a language model to supervise a multimodal model, potentially one day we are able to build a model that can understand the universe or the cells much better than the human. And also, like, how can a generalist model supervise a specialist or expert model on a specific domain? Where our first initial attempt is to use React to do automatic customization, but it's much more than that. First, we all know that LLaMA-7B is much worse than GPT-4 in terms of math capability. However, if you give it very good math instructions, recently there are already works showing that those models can have after fine-tuning on those data sets, the LLaMA-7B can outperform GPT-4 in terms of math capabilities. And so we know that the same architecture have the potential to become a model that's more powerful than GPT-4. And those instructions actually comes from the human knowledge. And the question is, can the model find those instructions, or can the model find those knowledges itself? And if so, the LLaMA-7B should be able to customize itself to be more capable than GPT-4 in terms of math capabilities. And then the next question is, what if we use the same technique, but we replace the base model from LLaMA-7B to GPT-4? Can it outperform human in terms of math capabilities? And I believe this is a super promising direction that I would like to explore. Yeah, these are my publications during my PhD, some of the publications, and I'm grateful for all the collaborators, mentors, and my advisor. Yeah, thank you all for attending the talk, and I'm not sure if we have time for questions.
Thank you so much for the talk.
Yeah, thank you.